Good morning. Good morning, good afternoon. Welcome again to our YouTube channel. And this is a new video. A video that was recorded post the presentation. This is a presentation you can see on the date that it was given on Wednesday, October 19th at the Space Simulation Conference in Annapolis. It was a great gathering. It was very good meeting friends and colleagues. NASA, JHO, the John Hopkins Lab, and IST have done a great job in putting together a very nice 4 days conference. So I gave this talk on Wednesday as part of a session on new technology and new novel methodology for testing. It was the first of the day, so it was very interesting to have feedback and discussions also afterwards. But I thought it was a very good topic to bring to our channels. And of course, you will see at the end there is my email, there is the email of our website. If you have any question, if you want to know more, just do not hesitate. Contact, get in touch, and we can discuss and we can go into more details. So the talk was on the acoustic field of a DFAT test, and the idea is to present more of the data in the background that we have been working on over the past month. So I wanted to share with the community. So first of all, talking of acoustic test means to frame it in the context of spacecraft and space hardware qualification. And not in terms of vibration and pyro shock, which are the milestones, but in terms of the acoustics, of acoustic tests of space hardware. You can see how the image now has superimposed a speaker stack, these columns of speakers to the reverb chambers, because this is the whole point of the talk. There is two methods, these new methodologies that are being compared and discussed. So acoustic testing is a milestone, and as everything else in the space industry is obviously regulated and is framed in a wider context. And the launch authorities, Arianespace and the SpaceX, they do have a manual, a user manual, so a launcher manual, in which the tests are defined in terms of reference, in terms of profile, in terms of what to do and how to do it. For what concerns the acoustic test requirement, there are some major, it's a very interesting differences between the European launcher, so Arianespace, Vega, Soyuz, Ariane 5. These are the launchers that it used to be Soyuz, now obviously Ariane 5 and Vega are clearly and explicitly mentioning the word diffuse when it comes to the acoustic field. So this is something that I haven't found browsing and looking through the other launcher manuals, so the Japanese H3 or the Americans. I guess that the assumption is that the tests are conducted in a reverb chamber, and therefore, by definition, the field will be diffuse. Of very specific interest is actually the new launcher manual of Ariane 6. So this hasn't flown yet, and so it is interesting to see that what is here is the fact that direct field actually appears for the first time as a possible test mean. So this is pretty important, because it means that the launchers are getting to deal with direct field as a test mean. There is also another point here, the third bullet, for homogeneity of the acoustic field dispersion. This is a new added specification on terms of uniformity. Before there was no such thing. In the older manuals, the launcher manuals, there was a profile. So this is the full octave band, the level, and the tolerances of the profile. So these were the specification of the launcher manual. Now, I think that the question is pertinent. Why do we test and how we test? So we test for two main reasons. A, to simulate the wideband acoustic excitation that the spacecraft or the component experience in the fairing, and second, to measure and to monitor the vibration levels that this acoustic loading has brought to the structure. There are different reasons, different criterion to measure the vibration and to quantify the effect of the vibration levels. But these are the two main. Now, there's always been a debate, and there's always been interesting discussions between the acoustician that define the specs and the owner of the structure that actually have to monitor the vibration. And I've witnessed many of these discussions, and the acousticians were very concerned about the acoustic field, and then how many points have been measured, and how many fractions of dB there is different. But the structures and the owner of the component or the structure, they say, look, as long as it vibrates to the level and to the shape, as long as it excites the structures, the property of the field are not extremely of concern to me. So there's these interesting discussions I've witnessed between the two groups of people. Now, how do we test it? And I guess for 50 years now, 5 decades, we test them in this reverb chamber. These are quite big with this thick wall, like 3 feet, 1 meter wide walls, large chambers. So 10 by 10 by 15 or 10 meter by 10 meter by 10 meters, like over 1,000 meter cube is a standard, nice size, large reverb chamber. As a large European acoustic facility, the Leaf, this is Cannes, Sunnyvale, NASA Planbrook. These are all large test facilities in which the acoustic field is produced using a modulator that injects the sound pressure into the chamber, in which nitrogen in gaseous form is there to reduce sound absorption. They are isolated. They have a floor isolated from the rest of the building. So very expensive, very complex, very expensive to build and to operate. You have to wait for the gas to evaporate before entering the room. They work. They are, when the design of this room is done, they have incredible performance. They can reach 155, 160 dB of level inside, but they're expensive and very to build and to operate. So over the past 20 years, this new technology based on electroacoustic excitation generated using loudspeakers has been developed to not to replace, but to provide an alternative to the reverberant field. So is one of those technology that I define as a business-driven technology. It came out because saving money, not because the chamber could do something that now with the speakers we can do. Well, actually, with a decade of experience, we got to that level, and we'll get there in a second. So there are things that the chambers cannot do, and the DFAT can do, and vice versa, of course. But this new method has opened a new avenue, and definitely has brought need to make sure that people learn about acoustic testing, know what kind of data to look at, understands what kind of plots are important, because it's not as before and is the standard reverb chamber test where the average of some control accelerometers 4, 5, 8 would be superimposed to the reference, and that was it. So here there is more to look at. But before going into some more details, just to give you a little background, DFAT was introduced late of 90s. late 90s, and has been going through a huge learning curve. You probably have seen these in the previous video on our channel. But I think it's relevant to add that we are in 2022, and there's been over almost 200 satellites qualified. So this is something that shows how established this technique and these technologies in the States. I think because of the internationality of the conference and for rigor towards the audience and the subject, I think it is also important to mention that in Europe things have started a bit later, and I have to say that I've been driving these since 2011 in my previous position with another company, LMS, now Siemens. These have been going on until I left in 2020. So we did a lot of work with ESA. We started with the Sphere. So ESA, so the European Space Agency, is like NASA. NASA started a work on a handbook, the 7010, in 2012, and then it published in 2016. ESA has started a working group in 2018. We'll see when a handbook will be produced. But obviously, this is something that will be part of the community, an interest in the community to have a handbook. There's a lot of things that in the space industry, need to be documented and to be given guidance, especially new technology like this one. So in the process of over the past 2 decades, there has been a number of studies. So the engineers, the structures, the rocket scientists, the people that own satellite and components, they wanted to know, they wanted to have a feel of how good was this new test method. And obviously the only, or the best way, or the only way to do it was to compare the results of a chamber test to that of a DFAT test. And so there have been a few studies. So here, this is Thales Alenia with ESA that was involved. This is Thales Rome with the chamber. This is Lockheed and MSI comparing the responses on the European service modules in Palmbrook and at the Cape. So there have been a few studies, and again, there was a lot of new approach there. There was no much knowledge. The uniformity was being improved from CISO to MISO to MIMO there was a lot of ground that was being broken into new knowledge, but there is still less than we know today. So at the time, engineers accepted that the result measured in DFAT, albeit different, and then the curves are clear. They were different. They're not the same, but they're very similar. There is obviously a similar. This first mode here, for example, this first mode, there was especially low frequency. There was a lot less than we will see in a second, lot less match between reverberant and direct field. Yet it was assessed and it was quantified that these differences were good enough. So one of the major points that have been on our agenda to work on and to establish more clear understanding and to control it better was the diffusivity. And again, we've seen, not only because we've seen it in the requirement from the launchers, right? We've seen the acoustic field is diffuse, so they actually specified. But there is one of the reasons, or the major reason why this is important, is because the diffusivity is it comes into play in the vibroacoustic analysis. So the vibroacoustic, the fluid structure interaction, the vibroacoustic problem we're trying to solve here, is defined mathematically by this expression in which the response of a structure has a dependence on a factor called the joint acceptance, in which the value of the cross spectrum plays a role. So this G of U, V, and F, so this is the position and the frequency. So this is a cross spectrum density between between two positions. So what this equation basically says is that the cross correlation, the pressure between 2 points, is a factor that determines how the structure responds. Now, we will see in a second with one formula, very simple, how this cross spectral density is related to the coherence and to the diffusivity of a system. So that's why these quantities, or the cross spectral, the correlation between 2 points, has to be measured and controlled. That's why the MIMO narrowband has, we've been working on these to make sure that the field is controlled not only in terms of uniformity, which is given by the diagonal term of this matrix, so the auto power, so the reference spectrum, the profile on the auto power, but also and most importantly on the cross term, so on the cross spectral density, on the relationship between each microphone and another. So this is very important, and let's see why. So if you take paper and pen and you do some maths, starting from the equation of a theoretical diffuse field, you'll come to the conclusion that the coherence is expressed by this Sinc function. The Sinc function is a sine of kr over kr. So sine over x is a Sinc function. So the x in this case is the product of the wave number k by the distance between 2 points. So the Euclidean distance between 2 points. So this is the coherence expression of a theoretical or perfectly diffuse field. Now, when we do a test, we measure it, and we measure it as ratio. So we have time data, we have like a time history, and then we measure the ratio of cross terms divided auto terms. So this is the cross spectral density between x and y, and this is the auto power x and the auto power y. So this is the measured coherence. How does it look like? So these are data that Bryce Gardner from it was a JPL at the time, published on the launch of a Cassini spacecraft. So he measured, so these data measured the coherence, and he also superimposed the theoretical curve. And these are acoustic test data that we measured. This presentation, these plots come from Marco's paper. He presented Marcus Underwood another work on the pseudo velocity on the fatigue of the excitation produced by DFAT the day before, so on Tuesday. So I took that paper from him, this picture from his paper, and you can see these curves here. So these lines are this function here. This is the Sinc function, and these other lines. So this dotted line here. And here are the measured coherence, experimental coherence. Now, when I give this presentation, there were quite a few faces that were looking at me, staring at me almost blankly, because these are concepts that the average test engineer or test lab manager do not master. This is the Sinc function and theoretical diffuse field. So with that in mind, I've been starting to work about a year ago on trying to simplify that and to show that how we could use a much simpler way of describing these difference. And so the result was published in August at the Internos conference, a major international acoustic conference, and is summarized by these Sinc, or the Sinc indicator function, or SIF. Is basically nothing else than the difference between these two curves. So we know that this is the theoretical Sinc function. We know that would be measured. But again, understanding the Sinc function and plotting, especially wanted to plot different fields or different would become then not as easy to interpret and understand. And therefore, the usefulness of this function, which become now a function of 0 to 1, with 1 being, so if this difference is 0, So if these two curves are exactly the same, then this is 0, and then this function becomes 1. And so we can see how by changing frequency, by changing type of acoustic field, you have different curves which can then be plotted and compared one each other. For example, the red curve here, this red curve is the reverb chamber. So the reverb chamber, we know that has a low frequency, which is in which the field is not diffuse, and the smaller the chamber, the higher will be this region, and the bigger the chamber, the smaller will be these. And then as the model density becomes higher and higher, and then the field becomes diffuse and uniform, then obviously these measured coherence tends to the theoretical function. This becomes 1. The magenta, which is at the opposite extreme, is the case of what we call MISO, or multi-input single output. So where 24 microphones are used, or a number of microphones are used to create an average, but one drive is sent to all the loudspeakers. So that creates the most, the least incoherent, the most coherent field. So a field which is, by definition, very coherent, so coherence is very high, and so it's the farthest from this Sinc function, and so this becomes almost 0. So that's how to read this curve. So we want to have a SIF which is as high as possible, because that indicates the closest, the smallest difference to the theoretical Sinc function. The robustness has been proven not only using different test data, but also numerical simulation. So these are the cross-correlation function but simulated using FEM-BEM software, vibroacoustic analysis, VA1, Actron, NX. So you can just pick any, and the theoretical function that you come up with, it obviously the same as the Sinc function, because by definition that's what the vibroacoustic solver do, and therefore the SIF becomes 1. So this is just a very quick, just one slide to refresh, introduce the SIF. There is another video on our YouTube channels for the SIF, but it's a very immediate and simple way of assessing how close the acoustic field is to a diffuse field. This is now being very much embraced by the industry, and so there will be more and more of these plots to be seen. So with this theoretical and an overall background in mind, let's look now at some of the data that we collected and some of the experimental results. So the idea was to compare the response of this honeycomb. So this is a 8x4 honeycomb panel. Again, it's representative in terms of material of some aerospace structures. I have had this remark before. It's not as a complex, so we don't expect the model complexity or the structural vibration response complexity of a full satellite. But again, the scope here is to see how close these responses match between a reverb chamber. This was done in Goddard about a month ago in Goddard, and this is what we have done in our lab in Baltimore. Again, if this doesn't work, then if there is no match at this simple level of panel, then obviously, we want to think again on having a comparison. If we had put a very complex structures, then the question would be, okay, which part and where do we start? So I think we want to start with the simple panels. We're going to go up. We're planning to run another experiment, a similar experiment with a more complex little structures, the 3D structures. So yeah, I think we'll build some more knowledge, but the result that you will see are pretty clear on what to expect. So we run a test using our standard speaker circle, what we call it 8x8. So there is 4 pair of MP21, which are our subwoofer speakers, and 4 pairs of MP150, which is 3 ways. There were 24 control microphone placed in a circle. We tried to replicate the same geometry here, this position. As you can see, this is a totally randomly placed. So they go all the way above the panel, below the panel. So it's really a random cloud of microphone surrounding the specimen. Just we will see also in the next slide. There is a slight difference in the suspension system between the two. The two sandbags at the bottom are the same, but the top bungee cords have been replaced in the chamber by metal holders, so metal wires, and that is because of safety within NASA. You cannot hook something, hang something from a hook without a metal. So there was there is a little difference here, but again, nothing that would prevent. We're trying to replicate that. We'll run again another test. Also the height from the floor here was a lot closer, so we will suspend these really the way we did it at NASA. But the result, the main conclusion, will not change. We ran it using a standard profile. It was 138.5 dB. Again, the idea was not to blast it too loud. It was just to measure the field and the response. We used different MIMO targets. The MIMO matrix was different, and you will see in a second what that means. But in all the experiments, the average, which is very interesting, the average is very similar and all close to the reference. So the blue is the DFAT average, the green is the reverberant chamber average. So if we look at only the average, this is what the results look like. So we are on target within tolerances. So this would be a pass test. So there is no question asked on the validity. So let's look a bit more in the details of the data and the plots of these tests. So reverberant field test, standard usual plot that everybody has ever done an acoustic test would look at. A reference with the tolerances and an average of the control microphone. Everything is within tolerances, everybody happy, the analyst will get the data, will produce a report to the launcher, and the test is passed. What we usually don't do in reverb field tests or in chamber is to look at more details in each microphone. So some analysts might do it. There's some analysts that can do it. It's not uncommon, but it's not necessary for the qualification effort campaign. If we would look at each microphone, we would see that actually there is quite some difference here. So we do accept it. So we all know. So the community knows. And of course, the smaller the chamber, the higher will be this dispersion and the higher will be this frequency. For the biggest chamber, so the largest chamber, this uniformity starts a lot earlier. So this uniformity that we find here, which is like really a fraction of dB, will start a lot earlier around this frequency. So, but nobody questioned this. Nobody, we all know, and so it's taken for granted. After all, there is nothing we can do in a reverb chamber, right? So there is no. It doesn't depend on the controller. It doesn't depend on anything. It's the design. The size is what it is. So the other quantity that we don't look at in the reverb chamber, because we are assuming that is for granted, is the diffusivity of the field. But if you look at the SIF, it is true that in the higher frequency, then becomes the field is so diffuse that is basically approximating the theoretical curve. That's why this is one. This is the SIF, but in the lower frequency is not as diffuse as one could think of. And of course, the fact that the dispersion is so high means that actually the waves are not coming. So the definition of diffuse field is that the fields, so the pressure waves come equally from all directions. So there's no preferential direction here. So the result of the consequence of this would be a uniformity of the field. So we take uniformity as one of the requirements of a diffuse field, and the other one being that the Sinc function is expressed by the coherence expressed by Sinc function, which is the SIF here. So these two will tell us how diffuse is a field, an acoustic field. Obviously, here we know that it's not as diffuse in this frequency, but that we know. Now let's look at the result of direct field. Also in this case, the average, so the red curve and the blue curve is the reference. It would be by all standard an accepted and passed acoustic test. If this would be the only thing that we look at. So we would get the average microphone. We would plot on top of the reference, like, hey, look, it's a great test, great. Only that in direct field acoustic, there is still a lot of questions to be answered when it comes to project managers and to scientists and to analysts, and so they start asking a lot more questions. So we need to look at more plots because we need to justify more data. And the next plot that we look at is the uniformity. So here we plot each individual microphone. So this is 24 microphone. The black are the tolerances, the blue is the reference, and these are all these dotted lines are all the 24 microphones. Now you can see first of all how close these microphones are to each other, but most interestingly is how much closer these are in this frequency than the chamber is. So we are looking at how direct field acoustic test can produce, does produce a field which is a lot more uniform in lower frequency than the reverb chamber, because the direct field in the circle is a narrow band control that doesn't suffer from the limitation of the modal density and necessity of a reverberant field. So once we've seen how this is on top of the levels and the tolerances are met, the uniformity, each microphone is within tolerances, then obviously the next things that the question is, okay, how close we are to a Sinc function, and so that what can we tell about the diffusivity field? Now the Sinc function curve to the SIF, the Sinc indicator function, is obviously as close as it can be to a reverb chamber. So it starts at the same level and then it goes higher and is almost one, so in the higher frequency, and then that together with the plot above, so of the uniformity, then it shows how close we are to diffuse field. How this field that we produce nowadays is basically diffuse. So we can look at this uniformity in a different way too. Actually, we can look at the plot using the Ariane 6 criterion. So this is plus and minus 3 dB, and this is how far from the average each microphone is. So these are 24 microphones, and we can see this band they're very close, and it's in the lower band, of course, this is octoband, they're a bit farther apart. But this is how close we are to a reverberant field. So this is very small dispersion, so the field is very uniform. The waves are coming from all over the place. The coherence gets really close to the shape of a Sinc function. So this is really a very good approximation of a diffuse field. And these are the data you have to look at. Only looking at one is not good enough. It definitely doesn't tell the whole picture. And so almost anybody can come with this. The picture they've seen earlier is the same. Is actually the same. The same average, but the field is definitely different. So let's look at quickly at the response of the structure now in the acoustic field that we've been working on. So this is what is called the vibroacoustic gain, or this is the ratio of all the accelerometers mounted on the panel average. So that's the average of all the accelerometers divided the average of the pressure. So it's a ratio of G over Pascal, and gives you a view on the transfer function of the response of the structure. This is the reverb chamber, and as I was saying earlier, we did different tests. So the meso, the mid coherence, and then low coherence test, so the zero coherence test. So if you look at the response measured on the panel during the meso test, so with the least diffuse field, so with the field which has one drive, so it's very coherent, we will see, this magenta curve shows how far we are from actual, especially in the lower frequency, from the response in the chamber. So having the average, so if you look at the average response of these tests, you won't see much difference with the reference, yet the response is totally different. Then we can increase, we can start making the field a bit more diffuse by setting a mid-level coherence, a 0.6 coherence level, and then the green curve starting to get closer to the red curve. But then only when we use a diffuse field using a zero coherence value, then And again, zero coherence doesn't mean that zero coherence, but you know, when we set the coherence to be the lowest, then we get to a response which is as close as possible to that of the reverb chamber, of the chamber test. So this is the overview of how the two curves would, you know, they definitely look like each other. I will plot the same data now, but using the CIF as a reference. So the magenta curve is the CIF down here, so the lowest CIF, so the least diffuse field, or the farthest from the Sinc function, has the most different response from the reverb chamber. And the highest CIF condition, so the blue curve, has the closest to the reverb chamber. So obviously we have now reached the point at which the field that we produce in DFAT is, the acoustic field is as close as possible to the reverb chamber, but most important, the response is the same as the reverb chamber. Well, there have been, as I showed earlier, there have been studies in the past where the differences were not, they were there, but they were not deemed so big to invalidate the test. So they took it as a granted. You know, the DFAT has been approved years ago. We don't need to justify why. However, it is important to know that the technology that we have is now, we have developed, is now such that the field and the response in a DFAT can be that of a reverb chamber, or very close to that reverb chamber. So I think this is important to know. Surely you can pick another one of these curves. Surely you can approximate even more. But the question is, why would you, if we can have a response and an excitation which is the same as the reverb chamber we all work with? So this brings me to a set of conclusion or, you know, interesting statement of discussion. So first, we have introduced the CIF as a singular gain function that allows quite immediately, actually, is a 0 to 1 function. 1 means that there is no difference between the measured coherence and then the Sinc function of a theoretical diffuse field. So it's actually a very efficient indicator, very, very simple to realize how far we are from the Sinc function. These, together with uniformity, will, you know, to see that the field is uniform means that the waves come from all over the place, from all directions. It does give us a high confidence that the field that we are producing is diffuse. How do we do that? By using a MIMO control strategy that, you know, allows to set both. So the auto power and cross power density quantities. One is the target, so the main diagonal, and then one is the cross diagonal, so the relation between 1 and 2, 1 and 3, 1 and 4. So all of these terms are set as a target and then controlled using MIMO rectangular closed loop and adaptive control. Of course, if we wouldn't do that, then we wouldn't know what the coherence is between the two points. And Gordon Mass at Johns Hopkins Lab back in 2012, they did an interesting, so after that MSI introduced the MIMO square control, Gordon Mass and the team made a very interesting exercise of comparing reverberant and direct field, and they showed how the MIMO control improved uniformity but also coherence. And at the time there was not a specific way, or, you know, there was not yet a full developed way of controlling the diffusivity and the coherence of a field, but how the MIMO control result produced a coherence which was closest to that of the reverb chamber. One of the sentences in that paper that I still remember is that having a zero coherence, so a too low coherence compared to the reverb chamber, it's also not desirable, simply because that wouldn't be a diffuse field. So having if you take data, always look at the data. If 2 points have zero coherence or very low coherence, means you're not doing a good test. You're not approximating the diffusivity, the diffuse field that you're required to, you're asked to obtain by the launch authority. Again, whether or not this diffuse field is the right thing is almost a philosophical question. We do know that in the fairing, the field is not as diffuse as we are asked to produce, but at the moment that's what the launcher know, that's what the legacy test tell us, that's what the knowledge tell us. So at the moment, as provider of test facility and test technology, we have to provide the best way of obtaining that. Now, in the futures, we are spearheading any efforts of improvement and research for new fields. We have the tools. So as somebody told me during my postdoc, says, Alex, you can only operate and you can only work with the tool that you have in your toolbox. The more the tool that you have, the more things you can do. So our control, our system, our technology, our capacity is definitely a very complete set of tools, and it will allow us to shape the field. Unlike a reverb chamber doesn't have any tool. The reverb chamber is just a volume up and down. It can be very loud, and is by default it is what it is. So if one day we realize that actually the field in the fairing is not that diffuse and we have to change it, you cannot do it in the reverb chamber. So there is no much we can. There's no many levers and parameters we can change. However, in a DFAT, then there's a lot of things we can do. So this is a lot more versatile system. To conclude on the point that I made earlier, there is zero incident or failures that have occurred over the past decades, and 180 satellites qualified. So DFAT is definitely a safe, a proven way of testing. Of course, there is skills that is required. We have developed hours and hours and hours of testing, so there is nothing, and there's very little can go wrong. Actually, never went wrong. Nothing ever went wrong, given the experience we have accumulated. And this is because the tests that have been carried out on small, big, large, different loading base has given us a very strong base and experience. This is something that the program managers appreciate very much, because they appreciate it because it saves a lot of money. It's simple. It's a lot of money saved. When you have to bring a satellite to a facility which is far away, and you can save money by being in-house on site, is a lot of money saved. So, and it's true that there could be a difference. There could be a difference between the fields in the reverb chamber. There could be a small difference. We cannot have exactly the same, because otherwise it would be the same test. So this is obvious. But the difference in cost definitely justifies the small difference in the response and the vibration. But again, today we have really made a difference very small with our system. Takeaway message for you when you leave. So that's what I was telling at the conference. Is that having a loudspeakers and microphone doesn't make a DFAT system. So we've been patenting over 15 technologies to reach the level where we are. We have done tests on the major programs, defense, science, telecommunication. We have accumulated hours of experience, and the data that I was showing you are clear. So look at the data. So always look at the data. The good thing is that there is more, that there seem to be, the industry is asking for more. There's be more people that wants to offer this type of services or this technology, but mastering and it becomes now a learning curve that each of us has to go through, because looking at only the average is not good enough anymore. So it's not like a reverb chamber. So it's something that we are teaching, we are disseminating how to approach these. And if one system like ours, I've shown you one system. We didn't change anything in the setup. We only changed a few parameters in the controller. We achieved 3 different fields with 2 different responses. Now imagine if different systems will do that. So you have really you need to look at the data basically. So look at the data, nothing will go wrong. This is a great technology, and then the industry is obviously appreciating it. Handbook have been written, methods have been developed, so this is definitely something that it will continue and it will expand over the next decades. We just need to look at it with more critical and an expert eye. I thank you for your attention, and again, visit our website. This is contact details, ask questions. This is what I finished. This is the talk I gave as I finished at the conference. However, there was a topic that was brought up in the. I had it as a backup slide. I had some backup slides that were trying to address a potential discussion on a different topic, but I ran out of time. 20 minutes was enough, just enough time to go through these. So what I wanted to now give is the two slides that I had as a backup slide, because there has been a topic that was brought up which is very important and concerns the vertical. So we've been talking about diffusivity, right? So how important is diffusivity and why we should look at diffusivity and how we can look at diffusivity, the SIF. And this is true, this is important. And one of the topics that came out, and this is for us in the industry, has been known for a while now. So we've been studying it, we've been addressing it, and is the fact that these type of loudspeaker is called line array. They call it line array. They have a subwoofer in a stack and then three ways in other stack. So the claim is that these type of arrangement cannot produce a field which is as vertically, which is as diffuse in the horizontal direction as it is the vertical. So here you can see that if you put the microphone around here, so in the horizontal direction, that's where the waves come from. Then if you come this way, then you can have a certain diffusivity. However, vertically, these cannot be varied. And so you have a lot less diffusivity in the vertical direction. So per se, the claim is, yes, it's been done in the past. It's been brought up by, it was a Quartus paper many years ago. So it's been obviously at the attention of few specialists, but you need to really know the subject to brought up this level of details. We have then gone out and show that this is not this is something we know, we understand, and we can master. So these are geometry. These are microphone. This is the circle. This is the view, the plane view. So X and Y, and this is the Z view. So this is Z. And then it's X and Y. So you can, first of all, it is interesting to look at this picture. You can see the cloud on microphone. So this is, you can see that the test article is here in the middle. Here in the middle is the test article. And see, this is a cloud on microphone all around. This is 24 points. So when we look at uniformity plots, just bear in mind that you're looking at a uniform field all around these. There's a lot of points. So the field is very uniform. It's not just 1 point or 2 points. Now, there's a lot of points of uniformity. That's interesting. The other thing is that the microphone are in plane. The 24 and 12 are put at the same height from the floor. They just horizontally divided. So when we look at the coherence and the diffusivity on these 2 points, this is a good indication of how the horizontal diffusivity is. And on the other hand, the mic 1 and 29, so mic 1 is here. So there is a 4 meters above this. There is another point called 20, actually not below this. So this is on top, and below this is microphone 29. They have the same X and Y, but Z is a lot different. So this is more vertically separated. And sure enough, we done this the same also in the reverb chamber. We put the microphone on top of microphone 12 and 18, of microphone 18. And you can tell in the reverb chamber, whether you look at the horizontal spaced microphone or the vertical spaced microphone, the SIF, which means that how close they are to the Sinc function, is pretty much the same. And anyway, there's not much we can do. That's the reverb chamber. That's what it is. That's what the result is. The DFAT is obviously quite different. And it's quite different because the top plot here is the SIF, so how close to the Sinc function and diffuse field is in the horizontal direction. So these are the couple, this is the pair 12 and 24 that you've seen in the previous picture. And these are, doesn't matter how we drive it, what is the technology or what is the strategy that we use to control the field, they are pretty much the same. So the SIF and the diffusivity doesn't change in the horizontal direction. On the other hand, the red curve, which is the standard way of using it, if we didn't do, the old way, let's put the old way, or the standard way of driving, it is true that in the vertical direction drops a lot compared to horizontal. There is a dip in the diffusivity if we look at the vertical pair. However, by using our technology and control of the field, we can achieve a very diffuse field also in the vertical direction. So it's not the line array that prevents the diffuse field. So this is something we have to be very very careful when we listen, when we talk. Line array can produce the same vertical field and horizontal field. Obviously, there is always a trade-off. When it comes to uniformity, to diffusivity, there's a trade-off between power and field characteristics. There's always how many microphones. So there's a lot of things to. But the line array, this is just to show that line array can produce field, can be controlled in the vertical and horizontal direction to produce a uniform field and diffuse field, just as a reverb chamber. So that's all. So thanks for taking the time to listen to us and to leave comments on the channels or emails or website. We'll be following up any request, any additional comments that you would like to have, and we'll be posting new videos. So stay in touch and come and see us. Bye bye.